So when you look at L'Hopital's rule problems, I guess a couple situations occur that are worth note. And let's go through both of these situations here to see them like described in concept at least. Because in order to apply L'Hopital's rule, you have to have an expression of the form 0 over 0 or infinity over infinity when you initially evaluate. If you don't evaluate to 0 over 0, or if you don't evaluate to infinity over infinity, then L'Hopital's rule doesn't apply. First, let's talk about a case where on the surface it appears that L'Hopital's rule doesn't apply. But if you manipulate the expression properly, then you can make L'Hopital's rule apply. So imagine you had a case where whenever you evaluate, you get 0 times infinity, either infinity times 0 or 0 times infinity. The order, of course, in which you multiply doesn't matter. Now, on the surface, this does not look like it's of the form for L'Hopital's rule. Because to be in the form of L'Hopital, you have to have 0 over 0 or infinity over infinity. And we don't have that here. We don't have any division going on. But here's the thing to think about. There are two things you could do here. You could take this expression, and now here's the thing, like to process. Take something that is infinite in value. What if you try to take that to the denominator? Because let's say we left the 0 upstairs, and imagine we tried to take the infinity into the denominator. If we took the infinity to the denominator, taking infinity to denominator, the infinity would show up in the denominator as 1 over infinity. But what is 1 over a very large thing? 1 over a very large thing is practically nothing. So this would be the 0 over 0 case in disguise. So if you've got an expression upstairs that is an infinity adjacent to a 0 being multiplied, if you rewrote that thing that evaluated to plus or minus infinity as 1 over infinity and wrote it in the denominator, you would be equal to the same thing. You'd be saying exactly, because dividing by 1 over this thing is the same as multiplying by that thing. But what you now do is you manipulate the expression to be of the form 0 over 0. And now L'Hopital's rule applies. What about the opposite case? I mean, what about if instead of taking the plus or minus infinity to the denominator, what if you want to be taking the 0 to the denominator? Well, you could do that as well. Leave the plus or minus infinity upstairs. The denominator would become 1 over 0. But now 1 over 0 is not mathematically defined, but if you think about this, whoa. If you think about this in terms of limits here, when we're looking at a limit, the x doesn't actually equal a, it just approaches it. So we might not actually equal 0, we might just be approaching it. But as the denominator of the fraction gets very small, the value of that fraction gets very large. And so this could be rewritten as a plus or minus infinity over a plus or minus infinity. Because 1 over 0 is in effect an infinitely large thing. Now, whether it's positive infinity or negative infinity would take inspection, but that's actually not important when it comes to L'Hopital's rule. When it comes to L'Hopital's rule, the fact that you are infinite at all and in the denominator under something that is infinite in the numerator means that L'Hopital's rule applies. So one situation that could come up, and like let's just take an example here. What would this be? Let's say limit as x approaches infinity of x times e to the minus x. Here's an example of a situation where whenever you evaluate, this evaluates to infinity times e to the minus infinity. That's taking 1 and dividing it by e infinitely many times. That's going to be 0. So here would be a case where, as a first order of business, you might try to rewrite this you might try to take one of those factors to the denominator, because in fact, it doesn't matter, remember, from what we analyzed here, it doesn't matter which factor you take to the denominator. You could either rewrite this as e to the minus x over 1 over x, which actually looks kind of clunky and cumbersome. Or you could also rewrite this as x over e to the x, which looks a lot simpler. We'll see an example. Actually, we'll do this exact example in the next video, but I want to first address the second sort of particular that comes up in L'Hopital's rule that we have to be conscientious of. So one particular that shows up is instead of maybe having a ratio 0 over 0, infinity over infinity, you get infinity times 0, in which case you've got to move one of those factors to the denominator. When you do, whichever factor you move to the denominator, you'll make either 0 over 0 or infinity over infinity, and L'Hopital's rule will apply. What's the other particular that occurs? Sometimes L'Hopital sometimes is needed multiple times over. So what would be an example of that? And well, I guess here's the thing to think about. What if, let me just describe this as well in concept. So imagine you're working with this limit, and imagine it originally evaluates to 0 over 0. Well, if you evaluate to 0 over 0, or infinity over infinity, you could apply L'Hopital's rule, and if you did, you'd get the limit as x approaches a of f prime of x over g prime of x. You just take the derivative on top and bottom. But now, imagine this. After you took the derivative, evaluates to 0 over 0. Well, if this evaluates to 0 over 0, then L'Hopital's rule applies to this, and we could take another derivative. So we could take derivative of top and bottom again, and now maybe this guy evaluates to something clean and nice and simple, and you're done. Or maybe that evaluates to 0 over 0, in which case you need to take another derivative to use L'Hopital's rule again. But the idea here is that L'Hopital's rule can be applied multiple times over. An example where this would come into place, we saw in that last problem of limit as x approaches 0 of sine x over x. What if we had sine x over x squared? Well, we had sine x over x in the last video, and we took the derivative downstairs. We went to 1 initially, and then now we no longer had 0 in the denominator. Note, the first time you take the derivative here, you're going to have a 2x downstairs. That's still going to be presenting a problem, and then you'd want to take the derivative again in order to resolve the situation fully. Okay, but long story short, two particulars. We'll see both of these particulars through examples in the next problems. In fact, I'll leave a bit of the board up here to describe these things, but if you've got an infinity times a 0, pull one of the factors to the denominator, and you make something of the form where L'Hopital's rule applies. And if you get something that evaluates to something where L'Hopital's rule applies, and when you take derivative, you get something again that evaluates to something that L'Hopital's rule applies, well then keep applying L'Hopital's rule, and well, you'll get there. Because let me be very clear about this. On this test, this is the only thing related to limits that's going to show up on this test. So you can bet that whenever you see something on this test that relates to limits, it's going to involve L'Hopital's rule. So that's actually something in your favor here in terms of just sleuthing the problems that are going to be on this test related to this concept. But let me just stop talking, and we'll get examples up in the next video.